Hello everyone and welcome to the talk about foundations of ring sampling. I am Victoria Ronge and this is joint work with Christoph Egger, Russell Lai, Dominic Schröder and Huber Yin. First of all, what rings are we talking about? The rings we are talking about come from ring signatures. So on the one side we have a ring with Alice, Bob and Carol where Alice is signing. On the other side, we have another ring also with Alice, Bob, and Carol, but now Carol is the one who is signing. And now a ring signature wants to make sure that I cannot tell from the outside if Alice is the actual signer or if Carol is the actual signer. And why we are talking about ring sampling is that for the ring, at least in some contexts like anonymous cryptocurrencies, I don't use every possible signer there is, but I have to make a certain selection of possible signers. And this selection process is what we call ring sampling. Now, the most common cryptocurrency with ring signatures is Monero. And they do exactly what we do with ring signatures. They hide the actual spenders. We call them spenders as they spend the money, not signers anymore, and hide them within a set of decoys, so the other ring members. And this decoy selection was prior to April 2015 done by uniformly choosing other ring members. So when I want to form a ring, I fix my ring size and then uniformly choose other ring members. But this has the problem that the newest account, according to age within the ring, has the most probability to be the actual spender. The reason for that is older accounts that have been there for quite some time had a much larger chance to already really spend and not just be decoys. So after some alteration, finally, decoy selection from fall 2018 on is now done by a gamma distribution. And we will show that if the probability that someone really is the signer and therefore is the one who wants to create a ring in that sense at a certain point in time, then it's actually good to use this distribution. How do they come up with the gamma distribution? There is a paper by Moser et al. Where they analyzed Bitcoin data and also Monero data, which is older, where they could deduce some actual signers. And from that, they fitted a gamma distribution into that data. But now, what do we mean by the distribution is good? And how do we define this? So in other areas, we use already entropy to define such things. This is used in mixnets and also in anonymous communication, for example. And this provides us a number that we can actually compare between different ring samplers. And it also is similar to the advantage we normally have in cryptographic games. So when we say we have a certain anonymity according to our entropy, we can translate that the adversary has a certain advantage when it has to decide who is the actual spender within a ring. And to do that, we use guessing probability, which in the end will lead us to min entropy. So my guessing probability of a random variable x is simply the maximum of all probabilities which values x can take. And in our context, this means we have a set of spenders, and we just have a look at which of the spenders is the most likely one. And with this guessing probability, we can build the average conditional guessing probability of a random variable x given y. And this is the sum over all possible values y can take, multiplied with the probabilities for my x, depending on this particular y. And again, in our context, we have x as the spender or the spenders, and y is the ring. So we want to know the probability given a ring that each of the participants in the ring is the actual spender. And we sum over all possible rings which contain the actual spender. And this is a somewhat pessimistic measure because we always take the maximum, and we also assume that we have honest spenders. The reason why we assume that is, in most of the cases, it's the best idea for an honest spender to choose according to the distribution given by the system, because it is assumed that the system means well for everyone, basically. And from this guessing entropy, we get our min entropy of x. And the min entropy of a random variable x is defined as the negative logarithm of the guessing probability of x. And again, we can have our average conditional min entropy of x given y. And this is then the negative logarithm of the guessing probability of x given y. And this provides us, as probabilities are between 0 and 1, with a value greater than 0. And with this now, we build our new anonymity measure, depending on our spenders and our ring sampler. And we say this is the min entropy of S conditioned of the output of the ring sampler when input with S. This has a very nice property. That is, if we assume a distribution and we are slightly off with this distribution. And slightly off means here that the linear divergence is smaller than a certain epsilon. Then we can show that the anonymity measure of the one distribution of S is greater or equal the anonymity distribution anonymity for distribution S prime minus epsilon. So when we are not exactly seeing the probabilities for each spenders, but more or less good enough, then we know that our anonymity measure also is not far off. And we can see that the measure makes sense by first having a look at two edge cases. The first edge case would be that I simply really use every possible spender within the universe. Ring signatures normally don't do that because of implementation, but we could assume that it's possible, and then the anonymity of such a ring sampler, which is basically Zcash, is the negative logarithm over the maximum of all probabilities for each signer. And that's here the best we can hope for. I cannot do anything better but just saying, okay, I am the most likely, well then I am the most likely, but I cannot change that. And the other edge case, that's the one sampler. So my ring sampler for a spender always outputs just the spender as ring. And there, of course, there should be no anonymity at all, because if there is one ring member and one spender, this has to be the actual spender. And with our measure, we get the negative logarithm of 1, which is 0, so we know that it's a quite bad sampler. Some intermediate cases are first the uniform sampler. The uniform sampler is what I already explained for Monero. We just sample uniformly over all possible spenders the ring. This gives us some binomial coefficients, and depending on the probability for the actual spenders. And we can see that if spenders are actually distributed uniformly, then this would be quite good with the uniform sampler, because then we get the logarithm of n, so of the ring size, as anonymity, and that's optimal. That's the best we can hope for. And on the other side, if our distribution is exponentially, then this anonymity tends to 0. So it's quite bad. This again shows us if my idea of what should be the distribution and I'm choosing a sampler accordingly is close to each other, my anonymity gets good, otherwise bad. And we can see that also if we compare some data. So this is produced data in the sense that we just draw a lot of sample rings with the according distributions. And we have our uniform distribution for the spenders, which of course are optimal. And then we use a baseline distribution for different universe sizes T. And we see that with increasing universe size, the anonymity even gets worse. And what do we mean by baseline distribution? We did the same as Mirza et al. And fitted a curve into Bitcoin data. But we think that a shifted Pareto distribution is slightly better according to the values we got. So instead of the gamma distribution, we use a shifted Pareto distribution, which still provides kind of similar values. The next sampler one could think of is the mimicking sampler. That means I'm sampling with the same distribution I assume that the spenders have. This is what is tried in Monero currently with the gamma distribution. We assume the spenders have the gamma distribution, so we sample accordingly. And in our paper, we proved that the anonymity for such thing is greater equal a logarithm of n half if my initial entropy for my spenders was good enough. And now this logarithm n half might not sound that good, but as I said, it's a lower bound, which we could prove. And if we see now empirical data, again, we made a lot of sample runs, both for the baseline distribution we found and for the gamma distribution Monero is using, and as well for the uniform distribution. We see that when we just make samples, it's quite good or near optimal, with different ring sizes, which is L, and different universe sizes, which again is T. So while the proven bound is only logarithm half, we see that in reality it most likely is very good. But it's hard to achieve such a mimicking sampler, because that would mean we need to know very well the actual distributions of our spenders. And for this reason, we proposed a partitioning sampler. The partitioning sampler does the following. We first partition our universe in a public manner. And for us, we just say we distribute for age. So age is when an account appeared in the blockchain in Monero. And we just say we have a fixed partition size starting from the Genesis block. And then every partition has the same size. And new accounts where the partition is not full, so to speak, have to wait a little bit. But this seems fine because that's the same what currently happens in Monero. And when we now have such an outer partition, we partition further into our rings according to some public randomness, might be the hash over some blocks. And with that, we get equally distributed rings. And these are also publicly verifiable. So an adversary has to comply to the sampling process, which makes black marble attacks a little bit more difficult because I cannot say initially in which ring will my black marble end up. And so it's more difficult to insert it. And this now assumes that we have a uniform distribution within each partition, not over the whole universe, but only inside one partition. And this means that accounts of a more or less the same age, which are very close in terms of age, have the same probability. And this seems reasonable because age is something we can determine, but it should be the only thing we actually can determine for a spender. So yes, of course, we can distinguish between different keys and between different spenders, but this should not be that we can distinguish in another way but age. And for age, they look the same because they are in the same block or one to the next. So it seems reasonable that we can assume if the partition is small enough, we would get more or less uniform distribution. And if we have this uniform distribution, we also have, again, our perfect anonymity within the partition, which is logarithm of n. So in the end, the measure works quite good. And if we are more or less sure that we have the right distribution, we can give a quite good estimation of the anonymity of our sampler. And even if we are slightly off, in the end, that's not too bad because our anonymity won't change too much. Get better data for our anonymity, but by definition, this would mean that we reduce the anonymity of current spenders, so the current existing transactions. Therefore, on the one hand, it would be very interesting. On the other hand, of course, for the actual users of the cryptocurrencies, this wouldn't be that nice. And with this, I thank you for listening to the talk.